Uranium, a seemingly ordinary natural element that possesses extraordinary power. Just one small uranium particle is enough to provide energy for an entire neighborhood for a year, clearly demonstrating its enormous potential in the energy field. The journey to discover uranium is associated with major turning points in 19th and 20th century science. In 1896, physicist Henri Becquerel first discovered radioactivity while studying uranium. This discovery opened up a completely new field of science, and soon after, Marie and Pierre Curie continued their research, separating other radioactive elements such as radium and polonium, laying the foundation for modern nuclear physics. In 1932, James Chadwick discovered the neutron, a neutral subatomic particle. The existence of the neutron helped scientists gain a deeper understanding of atomic structure and paved the way for important later studies on nuclear reactions. A revolutionary milestone occurred in 1938 when Otto Hahn and Fritz Strassmann, with the crucial explanation of Lise Meitner, demonstrated that uranium atoms could undergo fission when they absorbed a neutron. This process released a huge amount of energy and many other neutrons, starting a chain reaction, the core principle of both atomic bombs and nuclear reactors. From a natural element that had little attention, uranium became the center of science and technology, opening the era of nuclear energy, both full of promise and containing great challenges for humanity. Uranium is a naturally occurring heavy metal consisting of many isotopes, the two most important isotopes for energy applications being U₃O₈ and U₃35. In uranium ore obtained from mines, the majority is U₃38, about 99.3%, a relatively stable isotope that is difficult to induce controlled fission. In contrast, U₃35 accounts for a very small proportion, only about 0.7% of natural uranium, but it is U₃35 that is likely to fission easily when it captures neutrons and releases energy. Therefore, to fuel most commercial reactors, one must increase the proportion of U₃35 in the material, a process called enrichment. The level of enrichment depends on the type of reactor. In most commercial reactors today, the proportion of U₃35 is raised to about 3 to about 5%, enough to keep the chain reaction stable and efficient. Enrichment does not create chemically new uranium, but rather redistributes the isotopic ratios, making the fuel stream more fissile. Enrichment requires careful technology and control, as it is a key step in safety, security, and the management of the nuclear supply chain. In short, the natural properties of uranium, high in U₃38, very low in U₃35, are what makes enrichment necessary. Only by increasing the U₃35 ratio to the appropriate level can uranium become useful as fuel for commercial nuclear power reactors. Increasing the U₃35 content of uranium, that is enrichment, has gone through several technological stages since the mid-20th century. During World War II, the Manhattan Project experimented with two main techniques: gaseous diffusion and electromagnetic separation. Gaseous diffusion uses semi-permeable membranes to separate UF6 molecules by mass. Electromagnetic separation uses magnetic fields to deflect isotopes of different masses. Both work, but are energy-intensive and power-hungry, making them suitable only in times of war and with huge resources. The real turning point came in the 1950s with the development of the gas centrifuge. Centrifuge tubes spun at extremely high speeds, creating a powerful centrifugal force that forced the heavy isotope, U₃38, outward, while the light isotope, U₃35, concentrated near the axis. Thanks to their higher efficiency and much lower energy consumption than diffusion, centrifuge systems quickly became the industry standard. The design operates in a modular, cascaded manner to achieve the desired enrichment and requires precise balance, vacuum, and mechanical control. In terms of historical milestones, in 1951, experimental reactors using enriched fuel first demonstrated the ability to produce electricity. By 1954, the Obninsk power plant, USSR, was connected to the grid with nuclear power, marking the application of enriched uranium for commercial production. These advances not only improved efficiency, but also placed high demands on security, technology control, and global nuclear supply chain management. Uranium is a strategic material with an uneven geological distribution. The three leading global producers are Australia, Kazakhstan, and Canada, accounting for about 70% of total supply. Uranium extraction begins with geological exploration, followed by the selection of a mining method appropriate to the nature of the deposit. The three main techniques commonly used are open-pit mining, underground mining, and in-situ lixiviation, in which a chemical solution is injected into the rock to dissolve the uranium and then pumped back to the surface. After being removed from the mine, uranium ore undergoes a series of preliminary treatments at the processing plant. The first is crushing and grinding to break the rock into fine particles, facilitating further chemical reactions. Processing usually involves chemical extraction to separate the uranium from secondary minerals. The resulting solution is processed and precipitated, resulting in a distinctive yellow intermediate product called Yellowcake, oxyuranium. With a uranium purity of approximately 70–90%, depending on the technology. Handling, storing, and transporting Yellowcake requires strict safety standards, protective gear for workers, ventilation, radiation monitoring, and corrosion-resistant steel bottles to prevent reactions with moisture. Yellowcake is then transferred to a further enrichment or processing facility, a key link in the nuclear fuel supply chain. Once the Yellowcake, the uranium-rich intermediate product, is obtained, the next step is to remove impurities and convert it into a compound suitable for enrichment. Uranium hexafluoride, UF6. The refining process aims to increase the purity of the uranium, separating out excess elements and mineral compounds still mixed in the Yellowcake. This process is carried out in specialized facilities with strict safety and environmental standards. All operations include radiation monitoring, exhaust gas treatment, and worker protection. The result is uranium in a chemical form suitable for further conversion. In controlled chemical reactions at the conversion plant, uranium is converted into a derivative that can conveniently transition from solid to gas. The resulting compound, UF6, is volatile at listed conditions, which makes it suitable for use in modern isotope separation technologies. Due to the corrosiveness and toxicity of the fluorinated solution, the production, storage, and transport of UF6 requires specialized packaging in stainless steel or equivalent materials, strict humidity management, and a safety system against leaks. UF6 is stored in specialized steel vessels and is only transferred to the enrichment facility when it meets all technical and legal safety standards. It is the key link between uranium mining and the next step, isotope enrichment for use in reactor fuel. Overall, the refining and conversion stage is a complex industrial process, subject to strict technical, environmental, and security controls. Uranium enrichment is the process of switching the ratio of isotopes to increase the percentage of uranium-235, the fissile isotope, relative to uranium-238. Essentially, the process relies on the small mass difference between the two isotopes. Industrial methods use physical effects to separate the lighter from the heavier. The technology is used under industrial conditions, in highly secure facilities, and is usually operated continuously to achieve enrichment levels suitable for commercial reactor fuel. Because of the high safety and security risks, all enrichment facilities operate under a strict legal framework, under the supervision of international organizations and national regulatory authorities with material controls, leak prevention, and security measures. The primary goal of civil enrichment is to provide standard fuel for nuclear power plants, while strictly complying with nuclear non-proliferation regulations. Once the uranium has been converted from its enriched gaseous form, UF6, to its oxide form, the next step is to turn that material into small, yet powerful solid fuel pellets. These pellets are typically the size of a pea, about 1 centimeter across and weighing about 7 grams. And each one represents the energy equivalent of a ton of coal. Once formed, each pellet undergoes a series of advanced quality checks. Diagnostic imaging methods such as X-rays and laser optical measurements are used to detect cracks, voids, or other irregularities in shape and size. The pellets that pass are precisely placed in zirconium, a light, strong metal that absorbs few neutrons, tubes, which are then sealed and assembled into complete fuel bundles, each of which weighs several hundred kilograms and is further inspected before being placed into safe storage. The entire operation process is carried out under strict security and safety conditions, under professional supervision and strict regulations to ensure fuel quality as well as protect people and the environment. Inside the reactor, fuel pellets containing uranium-235 are at the heart of the power generation process. When a neutron hits a U-235 nucleus, the nucleus splits, fissions, releasing a large amount of energy as heat and simultaneously generating new neutrons, which in turn collide with neighboring nuclei, sustaining a continuous chain reaction. To prevent the reaction from growing out of control, control rods made of neutron-absorbing materials such as boron or cadmium are used to moderate it. Lowering the rods lowers the neutrons, slowing or stopping the reaction. Raising them allows the process to proceed more vigorously. The heat generated heats water in the main circuit, turning it into high-pressure steam. This steam feeds a turbine, which turns a generator and converts the thermal energy into electricity. A modern commercial reactor can produce over 750 megawatts of power, enough to power about 500,000 homes. The entire system operates under close supervision, has multiple safety layers and redundant cooling systems to ensure the reaction remains within safe limits. After about a year of operation in the reactor, the uranium fuel bundles have released most of their energy, but they are still extremely radioactive and continue to generate heat. Therefore, they cannot be directly disposed of. The first stage of management is to put these fuel bundles in a cooling water pool about 8 meters deep. The water here has a dual role: to cool the hot fuel and at the same time block most of the radiation emitted, protecting the surrounding environment. During this process, an interesting phenomenon often appears: the Cherenkov blue light. This is the effect when charged particles move through water faster than the speed of light in that medium, creating a mysterious blue glow. After many years in the cooling pool, when the radioactivity has decreased, the spent fuel is transferred to dry storage. They are sealed in thick steel tanks covered with reinforced concrete, capable of withstanding earthquakes, collisions, or harsh conditions. In some countries, old fuel is buried deep in stable geological deposits to be completely isolated for thousands of years, ensuring safety for future generations. Nuclear power plays an indispensable role in the global energy system today, accounting for about 10% of electricity production. The biggest advantage of this technology is the ability to generate huge amounts of electricity while emitting extremely low CO2, contributing to climate change mitigation. The journey from a raw uranium ore mine to becoming a nuclear fuel pellet in a reactor is a testament to the precision, strict control, and advanced technological level of humans. Each stage, from mining, refining, enriching to manufacturing fuel pellets, requires high technology and a multi-layered safety system. Thanks to that, nuclear power not only provides stable electricity, but also demonstrates humanity's conquest of science. However, there are still controversies surrounding the issue of radioactive waste and the risk of accidents. However, with increasingly improved technology and strict safety standards, these risks are being better controlled. In the context of increasing energy demand and pressure to reduce emissions, nuclear energy continues to be an important solution towards a more sustainable and greener future. Thank you for watching. If you find the video useful, Don't forget to give me a like and subscribe to the channel to motivate us to make more interesting videos.